All right, I see most people preview, so let's get the show on the road. Check mine. Okay. When I last stopped, I was dealing with the fact that there's this idea of relativistic mass. Einstein didn't like to call that, but Lewis will do it. And that as an object moves through space, it becomes more massive, its momentum increases, its energy increases, and that increased mass is basically the kinetic energy. That's where it's stored. Okay? I'm going to continue that first by knocking out a problem that finishes the second, and then by knocking out some problems that will finish the last third module. Basically, we'll be finishing up relativity. I'm going to go after that out of the book, so I'll send you some handouts, and I'm going to deal with the idea of probability and statistics. Quantum mechanics, in particular, deals with the idea of probability distribution functions, and my experience is students aren't that good at that, partly because you don't have 156-hour degree plans like I did as 4 years. Used to 18 hours was considered a minimum load, not 12, and that's pretty standard. There's a long history about that. But the bottom line is that you still have to cover the same material, whether it's covered in fewer hours or in more. So you don't have a course in probability stat in most of your degree plans. But you need to understand probability distribution functions, normalization, how to find means, how to find standard deviations, and so forth. So we're going to have to deal with that. Also, you don't get 3 semesters freshman physics anymore. You get 2, which means most people get shortchanged on entropy and energy. Well, that's a lot of where things in quantum mechanics came from, so you can't really understand the idea of black-body radiation and Planck's theory if you don't understand something about what was being done in that time. So we're going to spend some time on that. So I'll send you some stuff to expand on that. Most of it comes out of Rolf's more advanced modern physics book. I have left a copy, not to be taken away, but in the SPS room, which you can use. All right? So I'll put that, and I'll make you some copies and scan and send you some stuff via your email. With that being said, let's look at the first problem for the day. You have a particle. It is an unreasonable particle because you wouldn't probably have something this large. It says that it is 2 times 10 to the minus 8 kilograms. It's moving at 0.9 c with respect to observer 1. And what I want to do here is to just ask you to calculate linear momentum both by classical physics and by special relativity. So in classical physics, it's pretty straightforward. E is m naught v. I put the naught, we never did that in regular physics because there was no question, there was only one m. The m that you're given in the problem (2 by 10 to the minus 8 kilograms), and it's moving at 0.9, and for c we'll put in the value. And you just punch it. So whoopee, not much of a big deal, but and there really wasn't really much reason for a calculator because I made it where you could do that. So it's 6 times 0.9, so you should have got 5.4. And that's exactly what you do get. When I used to make a lot of these notes, my son was small, and he used to swipe my calculator all the time. So one of the reasons I made the things where you don't usually need a calculator. Another reason is I want you to concentrate on the physics and not how fast your fingers move. All right, I can train a tame monkey to type a calculator. You don't pay people for that. You pay them for thinking. So that's what classical physics says. Let's look at relativity. One way to look at it is that P is going to be mv. That's gamma P classical. So you're going to increase it by gamma. In our case, gamma Move it up a little bit. It's 1 over the square root of 1 minus 0.9 squared. So let's see here, we got 2.29. So if you fail to account for relativity, you're going to mistake the force by 229% error. Which means you will not get the acceleration you expect. You will not get the deflection you expect. Everything about what it looks as if it's 229% more massive than what the object from classical physics says. So if you had a 1 kilogram object, it would look like a 2.29 kilogram object. Now it's about 2.54 pounds of force. I'm sorry, 2.2 pounds of force is equal to about a kilogram of mass if you weight lift, as I do. So in other words, instead of lifting about 2.2 pounds, you'd be lifting about 5 pounds. Or instead of lifting, for instance, 40 pounds, you'd be lifting 100 pounds. There's a big difference between lifting 40 pounds and 100 pounds. All right? So failing to account for an object that moves at high speed means you're going to completely get everything wrong. This is not a small effect. And in something like the SSC or CERN, where you've got things going at 0.9999 the speed of light, you can be off thousands of times. So it will not stay in the range where you think, and you will not have the magnetic fields that you expect. Of course, you can punch this all in the calculator and get the final answer, which I don't really care that much about. Big thing is, make sure you realize that not only mass changes, but momentum changes. Okay? Now, this type of a problem where you calculate P works fine provided this mass, this object, has rest mass. It does not work for a photon. In particular, it's important to note that the formula m equal m naught over the square root of 1 minus v squared over c squared doesn't work for massless particles like photons. Because m naught is 0, and the bottom is 0, and you have 0 divided by 0. It's derived assuming the particle had rest band. We will deal with the correct formula today for how to deal with the photon, and as expected, the answer for that solution is the same as you get out of optics, which was the class right before this. It's E and M, because E and M did not have to be modified by relativity. So you can get it out of Maxwell's equations with a whole bunch of work in differential equations, or you can fall right out of modern physics with algebra. I far prefer the algebra approach. All right? But they are consistent with each other. Questions on that problem? Questions or preview? Anybody got a question on that problem?
No.
No, sir.
All right. All right, let's go on to the next section then. In the next section, we started looking at work and energy, and if you go back and look at your freshman stuff, you will find that the way the whole idea of this kinetic energy came about was out of what was called the work-energy theorem. And what you were looking at was you were looking for the network, which was the integral of the net external force dotted into displacement over some path. In one dimension, that's just dx. And that was still the sum of the external force. Now, Newton's second law says the sum of the external force is dp dt. Newton's second law in relativity says the sum of the external forces is dp dt, provided you put in the correct p. All right, it's not m not b anymore. classically, what we had was W net was M naught dV dt times dx over some path, whatever path you want. And we took that M outside because that M was constant in physics 1. You have to be careful that M is not constant. That M is a variable. It depends on V, and it may not be pulled outside the integral. Anything that was done after that is invalid. All formulas derived by that are invalid. And one of the formulas that was derived was kinetic energy is 1/2 mv squared. So there's no way to modify that formula by putting in the correct M, for instance, that'll make it work, because all the steps that were used to derive it are bad. So you can't just modify it at the end, like you can the P formula. Do not use kinetic energy as 1/2 mv squared in relativity. It will be wrong. Do not use P squared over 2. P squared over 2m. It will be wrong, because they're derived assuming mass is constant, and that isn't true. Now let me go show you just a couple steps. What they did is they took the dt and they moved it over. And dx dt was v. And then they integrated that. And when they integrated that, they got, that's just x dx. When you integrate that, you get x squared over 2. So when you integrated this, you got v squared over 2. So they got W net was 1/2 m naught v squared over 2 from the initial position to the final. And then they decided to call that thing kinetic energy. That was the final, that was the initial, and this was delta K, and they had the work energy theorem. But it's all based on Newton's law and being able to pull that M naught out. Newton's law is not a problem, but pulling the M naught out is. So none of this is right in relativity. What is correct is what I've worked out on the next set of pages for you, where I have not pulled the p's outside at any place or any time. I've left them inside the integrals, and I've applied what relativity told us about mass. So if you look through it, I don't plan to go through all of it because I expect that you should be able to read. I just did the dp dt. I moved the dt over just like in physics 1, and I get VdP. And my problem is you have to get one variable inside the integral, not two. So I need either everything to be in terms of P's, or I need everything in terms of V's. Well, one way to handle something to this when you have two different things is to integrate by parts. So if I integrate by parts, you're considering one of these to be a U and the other to be dV. And then when you integrate that by parts, you get uv minus the integral of v du from calculus 1. So I did that. I get a PV on this side, and I get this integral, and I replace the P with my formula that has V in it, so that all of my integral only has V. And then I know how to do that type of an integration. But one way or another, when you do an integral, you've got to get the integrated in terms of one variable. Okay? You can't have two. That's just what is required. Before you tack an integral, you must mess with the integrand. Now, I went through a bunch of algebra, quite a few steps of algebra, it turns out. I had to do a substitution to do the integration. I had to stick in some limits. I had to go ahead and do some more algebra to simplify. And after I did all of that stuff, I ended up with this final formula. Just doing algebra and calculus, no physics. And what it says is kinetic energy is equal to a quantity that's mc squared, where m is your mass in that particular frame moving. And this is the mass that you originally had times c squared. So if you look at it, you could factor the c squared out. So kinetic energy is due to a change in mass. So if you give something energy, I don't care how, you decide to build a nuclear reactor, you decide to shine light on it, you decide to put a burner on it, stick water on a stove. If you heat something, if you put energy in it and make the molecules move faster, you made them more massive. And if they're in a gravitational field, they weigh more. If you take particles and put them together, say you proton and neutron or electron in a proton. There's a proton, there's an electron. And you bring that electron in, and it gets bound. And it gets off light. As it gets bound into that well, that light is carrying mass. And the final mass of this atom, the hydrogen atom for instance, is less than the electron and the proton by itself. If you have a chemical reaction going, and that reaction happens to give off heat, it also lost mass. And it weighs less than it did before. This is facts. And yet in chemistry we use conservation of mass and conservation of energy. Why can we get away with this? The answer has to do with the c squared. If the energy is not too much, this number is so large that this is so small you can't measure it. But it still happens. Mass is a type of energy. I'll put it another way, energy is a type of mass. They are equivalent. This is Einstein's great equivalence equation of mass and energy. If I lose a little bit of mass, in a nuclear reaction, for instance, I multiply that by this number, which is 9 times 10 to the 16th, and I get a tremendous amount of energy, which can go to particles or anything else. It can go to light, it can go to particles. Those particles can slow down and turn that energy into vibrations inside a steam engine or whatever. This is why thermonuclear warheads work. This is why nuclear power plants work. This is why the sun works. The sun is getting less massive every day. It is giving off mass. That's what heats this planet. And this planet absorbing those photons gains mass. Whether you consider that normally or not. All right? So in some sense, you want to gain mass. People say, don't want to gain mass and weight. What do you want to do? Freeze? Okay, you want to gain some mass. All right. They are equivalent. So read that section in particular in the book very carefully and read the notes very carefully. All right? So that's one of the big concepts in this section. So let me go one step further with this idea that it has. If you rearrange that equation, you get this. We're going to call this guy here E. We're going to call this one here E naught. And this is going to give us a very important equation for working homework problems. And that's the formula that we're going to work and use all the time to calculate kinetic energy. I can give you the total energy, I can give you the rest energy, and you can calculate kinetic. Or I can have a problem in which I'm give you kinetic energy by a nuclear accelerator, for instance, and you know the rest energy, then you can calculate the total energy. But this formula is extremely important for solving problems. If I know the energies, then I know the mass. The rest energy and the rest mass are usually known. They're measured. For instance, I know what it is for an electron. For an electron, it's 0.511 million electron volts. For a proton, it's approximately 938 MeV. For a neutron, it's approximately 940 MeV. I will expect you to know those for tests. I will not expect you to know any others. Anything else I will give you. But I will expect you to know these three. Why? Well, if I know about an electron, its rest energy, then I can tell you if a system requires me to do relativity to do it. If I know the proton, same thing. I can tell you if the problem requires relativity or not. The neutron, same thing. We'll also need these later on when we do a little bit with nuke in your nuclear class. So there are certain numbers that drive the universe, and there's certain things you should know off your head. All right? You should know the speed of light. You should be able to tell rough dimensions of things. For instance, if you have something, a scratch, it's probably on the order of a micron. That's roughly the wavelength of light, half a micron. So if you can't see a scratch, it's because it's smaller than the wavelength of light. It is a submicron finish. If you're looking for cracks, you're going to use radiation that's going to be on the size of the crack you're looking for. If you want to look at atoms, atoms have an order of about 1/10 of a nanometer, something in there. So therefore you want nanometer radiation. You need to get a feel for basic sizes so that you can make rough rule of thumb estimates. All right? So certain things you should know. You should know the wavelength of light roughly. You should know roughly the size of an atom. You should know some basic masses of particles. These are things you should know the speed of light. You should know Planck's constant. These are things that should be built into you. Anytime anybody asks, you should be able to snap it off. Okay? These are things physicists know. These things engineers know. People who are not, don't. If you're going to play in the profession, you're going to play with the pros, you need to know certain things. A pro football player wouldn't ask, what's a football? If they ask that, they don't know play pro football. All right? You should know certain things too. These are three things you should know. So put them to memory. I'll give you some others as we go on that'll make you fast and make you quick. All right, in doing calculations. Know these three. I'm going to use them a lot. We do not use the mass of an electron in kilograms. Nobody in the right mind to measure the electron in kilograms. It's not the way you measure it. It's a damn small number. You have no feel for it. It can't help you do anything. Nobody measures a proton in kilograms. We do not use SI units in modern. We work in C. We work in EV for energies. We work in EV per C for momentum. If you try to do the other, you'll eventually get it right. But A, you need more conversions, and B, you will be much slower than I am in working a problem. You'll take hours for things I do in 20 minutes. All right? So learn to use the correct units for the problem. If you're working with a baseball's on the order of a kilogram. Then you work in SI. Chemists don't use SI because they don't work with a kilogram of material. They work with grams. They use CGS. And nuclear and atomic and solid-state physicists do not work in SI because, again, it's too big a unit. We work in these modified units, so get used to them. With that being said, I want to do one other one that I want to talk about, and that's momentum. So I spent a lot of time in the notes talking about what basic science is, the difference between applied engineering and basic physics. I also gave you one other really important formula. that we'll need in all the homework problems today. And that's this formula here. I like to call this the momentum formula. Notice there isn't just a P. It wouldn't have the right units. This has the units of an energy squared. Momentum has the units of an energy per C, so it needs a PC. Politically correct. You square the PC, add it to that, and you get this. Some people like to draw it like this, which isn't necessarily bad. They say, here's E naught. This is PC. And that's E. And it forms a Pythagorean triangle. And that's true, it does. You can think of this as a different type of space, an independent space, and consequently at right angles to this space, which is the rest mass space. If P goes to 0, if you're not moving, then energy is E naught. It also tells you something else. If the particle has a lot of momentum, and this side gets bigger, 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 then E is approximately PC. And you can ignore the E naught altogether. If its two sides are not very different, then you got to use the formula. At the stern, the momentum is so large that for all intents and purposes, you can ignore the rest energy. They have protons going at TeVs. The rest energy isn't even a GeV. All right? So they can just ignore this. Consequently, they talk about the energy, the momentum, and the mass being the same thing. They're not. But because they're so close, they only differ in units, it makes it easy for them to do that. It gets sloppy. They don't even put the units down correct. That's why they do it. I want to take these two formulas and I want to work some problems. So the first problem I'm going to do is the problem 1 in your notes. And I want to show you how to, even in classical physics, how some units can help you speed the problem. The problem says an electron has a kinetic energy of 0.1 MeV. Find its speed according to classical physics. So let me zoom in a little bit. When you see energy of a particle in a problem, they're talking about kinetic. That's the energy the accelerator or something gives it. Okay? It often doesn't say kinetic energy. It'll say you have a 2 MeV proton beam. That's kinetic. Protons have 938 MeV of rest. So they couldn't be 2 MeV. They couldn't exist. So it's kinetic. So I know this. I also remember this. And they've asked me to find this. First things first, find the total energy. E is E naught plus K. I'll show you why I want this in just a minute. Nice simple calculation. Now, classically, K is 1/2 mv squared. I'm going to put m naught just to remind me that that's the rest mass. This does not work for relativity. This is classical physics. So therefore, V is the square root of 2K over m naught. Now you have K in MeV. M naught, maybe you remember it off your head. It has to do that 10 to the minus 31 kilogram type thing. Maybe you do, maybe you don't, but you weren't given it. First of all, you wouldn't want to do this in kilograms because you'd have to change K and do conversions, and you'd have to know M naught. So what you're going to do is this. You want V in terms of C anyway. Put a C squared here. 1 over the square root of C squared, that's 1 over C. Put a C on top. That's just multiplying by 1. Now, I have 2k, but I have m naught c squared. What's that?
That's E naught.
Huh?
E naught.
E naught. What's E naught? What do you call it? What is E naught in words?
It's the rest energy.
The rest energy. I do not need to know the mass in kilograms or anything else for the electron. I've converted it to something I know off my head. Let's see, I have 2 times 0.100 MeV. And on the bottom I have 0.511 MeV. There's all your conversions. Fell out. I have 2 times 0.1 divided by 0.511. 0.626. Quick, easy. Be on the lookout when you have an m to multiply by c squared top and bottom so that you can get that to an energy. That is the quick way to handle a relativity problem. Do not plug in masses. Okay? Now, by the way, some people will say, well, you could plug in masses, and I will grant that. If you had plugged in the mass as this, 0.511 MeV per c squared. If you'd have done that, for m, the c squared would have moved to the top and come out just like I did anyway. Relativity calculation. The problem with classical physics is it's always going to overestimate the speed. You can see this if you put in k of 1. If k had been 1, you would have had 2 times 1 divided by a half. You'd have had almost the square root of 4, which is 2, and you would have said the electron goes at nearly twice the speed of light, which is impossible. All right? So this speed here is always going to be greater than the speed found by relativity. In the relativity calculation, we cannot use this formula. What we need is the momentum equation. So in the momentum equation, E squared is equal to E naught squared plus PC squared. We go ahead and solve that for P. PC squared is E squared minus E naught squared. So P is the square root of E squared minus E naught squared over C. Now, that's MV. So we can divide both sides by M. V is the square root of E squared minus E naught squared over MC. But I'd like the speed in terms of C. So I'm going to multiply the top and the bottom by C. So the top is E squared minus E naught squared times C. And on the bottom I have MC and a C, so that's MC squared. What's that?
That's the kinetic energy.
That's kinetic energy?
No.
No.
It's the energy.
It's the total or rest?
Total energy.
I got a total, I got a rest. Which is it?
It's total.
It's total because this is not M naught. This was with the P, so this is M. So I've got E, I got E naught. I have everything necessary to make the calculation. Couple of things to note. If E is very, very much greater than E naught, this is about C. But it can never exceed C. Because you're always going to be taking something away from E squared before you take square root. So this thing will never exceed C, as the kinetic energy formula for classical physics did. I do not know this formula off my head. I know how to get it when I need it. I know this. Everything else is just algebra. We go ahead and plug that one in. 0.611 MeV squared minus 0.511 MeV squared over 0.611 MeV times C. So second square root 0.611 squared minus 0.511 squared divided by 0.611, 0.548. A smaller value than you got by classical physics. You're off about 80 parts in 548, 590, let's see, 8 sevens is 560, so you're off about a seventh. More than 10% error. Okay? It can be significant. V is good for doing problems that teachers assign. Let me tell you, in relativity, we rarely ever talk about speed. Why? Because the speeds are all near C. And when you get near C, 0.99999 and 0.999991 aren't very different in V, but they're huge in P. And so you're trying to measure V, you're trying to measure something that's very hard to measure, small changes. But if you measure momentum or energy, you can measure large changes. So it is a poor thing to try and describe particles by their speed. What is better is to describe them by their momentum and their energy. And that's what high energy physicists do, and that's what people who do relativity. So people don't tend to ever find V. They tend to talk about P. That's a well-defined quantity. And this one gets so close to C that two particles you can't distinguish their V's, but you can easily distinguish their momentums. They're different. Now there is a way, of course, to do this. You could subtract it from C and take the binomial expansion and do some really fun stuff, but I'll leave that for a homework problem. The truth is, this is much more an educational experience. True physicists would be working up here. They would not be asking what's the speed. They'd be asking what's the momentum. Let me give you another one. This one's slightly different because it's from a quiz that I gave at West Point. So I have to zoom in on it. They call them WRITs at West Point. Written instructional exams. This one says, assume an accelerator is to be designed to produce a 2 MeV electron beam. Actually, that's kind of low energy for a cancer therapy system. In order to kill both benign and malignant tumors in patients. As chief design physicist for Acme Corporation, a subsidiary of Roadrunner International, you have been asked to supply answers to the following questions to your boss, Dr. Wiley Coyote, for his meeting with the hospital representative for Pig. First, what is the total energy of the electron? So how did I get that?
E naught plus K.
Huh?
E naught plus K.
E naught plus K. I agree. All right, so what's E naught? 0.511 watt, the units.
MeV.
And what's K?
2 MeV.
2 MeV. Boy, I mean, you just can't get any easier points than something like that. I mean, God forbid you leave those blank on the test. Okay? Nothing's going to get easier after that. What's the momentum? How do we calculate a momentum then? What's the formula? Where do we start?
It's the E
E squared minus E naught
E
squared.
squared minus E naught squared, okay.
Square root over C.
Square root over what?
That's C.
C. So we have 2.511 MeV squared minus 0.511 MeV squared over C. So I got 2.5 squared. What's that, about 6.25? And then you're going to subtract about a quarter. So it's about 6. You got the square root of 6. It's more than 2 and less than 4. You should be able to do these things in your head, at least a little practice, right? Which was it? And then we take 1.57. Now, if you look at this, 2.511 was so much bigger than this. It's about that.
Everything you square root twice.
Huh?
Didn't you square root it twice?
Did I square root it twice?
Yeah, you took the square root twice.
No, I took 2.55 squared minus 0.511 squared. Square rooted was 2.549.
Yeah, and then you took it the second time.
I took this. Yes, thank you. You're correct. I did square root it twice. Didn't realize I did that. Which I'm getting ready to, because so what I was saying, which I should have found out when I get done, that's so much bigger than this that the answer is about that. Not quite. It's 2.46 versus 2.51. So I'm off 6 parts in 246. Right? So that's about 2%. I could get you within 10% error without ever doing that calculation on a GRE by just realizing this is so much bigger than that, it's basically E over C. Be on the lookout for tricks and quick to be able to be faster, okay? 2.46. Again, notice what happens to the C. The C becomes a unit. A unit of momentum is an MeV per C. A mass is MeV per C squared. And an energy is MeV. And speeds are in C, in relativity. The C walks around like a unit, not like a number when you're in the basic system. What's the speed of the electron? Well, again, we have this is mv. So V is P over M, which is PMC squared PC squared, which is PC over E times C. Just playing around with some algebra. So V is approximately 2.46 MeV per C times C over 2.511 MeV times C. .980. So 2 MeV electron beam is highly relativistic in a LINAC in proton therapy at a hospital. So relativity is relevant in the medical profession. And failure to account for it causes problems. In fact, relativity with electrons is relevant for lots of things. All right? Even in a flyback transformer at 25,000 volts in a television set, relativity inside the plates is actually relevant. Electrons have a very light mass, and you can get high enough voltages in electrical systems to be required. Protons is a big difference. In a proton, because this energy down here would be 938 million electron volts, unless you're getting into tens of millions of electron volts, you're not going to be able to deal with relativity. And to do that in a single step, which cannot be done, would require 10 million volt power supplies. You can't build those. You have to build really tricky ways to get up to 10 million volts. You have to build Linacs or cyclotrons or something else. So for protons and such, unless you're in the nuclear field and you build a big nuclear accelerator, you don't deal with relativistic effects. But electrons, power supplies for electrons and electronics can deal with relativity. Which is why electrical engineers need to know relativity. And I had one more part to the problem, which was a multiple choice one. Actually, I had some more which I've cut off. One of them says, if you send an electron down a 12-meter long vacuum pipe, because you want to get the air out so it hits your tumor, will the electron believe that the pipe is 12 meters long, believe that the pipe is less than 12 meters long, or believe the pipe is greater than 12 meters long? So this is a kickback to one of our previous lessons. So what's the answer? Prairie View, what do we got? What's the answer to the problem?
B.
Does it believe this less? What's your reasoning for that?
Because it's moving at a,
Speak up. Speak up.
I don't know.
How about we just now pretend that there's some audio?
We don't know.
You don't know? Well, you got the right answer, so we need to have a reason, though. How do we determine who's the proper and the improper length measure?
Yeah, because the distance is going to be based on the electron moving, since he's moving at a speed that, compared to the speed of light. The distance is going to shrink for the electron.
But why? You said it sees it moving. Who sees who moving?
Well, from the electron's perspective, since the electron's moving, the distance is going to shrink, right?
Okay. Well, okay, from the electron's perspective, it's at rest.
Oh, okay.
Okay, it's at rest. What's moving? What determines? What do we have to put on the pipe to determine its length? A ruler.
Oh, the ruler thing. Oh, yeah.
Right. And so if the electron reached out and tried to grab the ruler, what would happen to it?
It would get a splinter.
It gets splintered. So that's why it's short. All right?
Yeah.
The person who measures the proper so-called longest length of the ruler is the scientist in the lab. So he believes that the thing is 12 meters long, but the particle believes it's less. Now this isn't so important for electron because it's a stable particle, but if you were at, for instance, Oak Ridge and shooting a particle, those particles can be radioactive and they have a reduced half-life. And so more of them would make it to the end than you might think, because they don't believe that they live that long, they believe your clock runs slow, or they believe the pipe is short. Either way. And this is good because it enables us to build radioactive beam designs, which are very important for future medical applications as well as basic nuclear physics. All the other problems in this section, the one about the relative electron, I've already worked. The one about the photon, I've already worked. The collision I'll leave for you, but I already discussed how to do it. The last thing I'd like to talk, and I will do it very, very shortly, is the discussion of general relativity that he talks about and the principle of equivalence. Einstein did not consider in his original work accelerated frames of reference, nor the force of gravity. What he is able to show in his general theory that expands upon this is the following idea. Consider yourself inside an elevator. You believe the laws of physics are the way they are. You don't know there is anything outside the elevator. Maybe you don't know anything that there's someplace, another universe outside our existing universe. If somebody was to come in with a spaceship and to grab a hold of this and start accelerating it forward, if you were to let go of a ball or your briefcase, although the ball would be stationary, as seen by an outside observer, you inside the elevator, because you believe that you're not accelerating, the floor coming up, as I would see it, would run into the ball. But you would believe that the ball accelerated downward and hit the ground. Einstein says there is no way to tell the difference. There's no way to tell the difference between an accelerated frame and a force. And he goes one step further. He says, look, if you shine a light, the light should go straight across. But if the elevator is accelerating upwards, while the light may go across it, as I see it, you will see the floor coming up toward it, so it will be as if the elevator saw the light bend. And he says, because I can't tell the difference between an accelerated elevator and a force, I claim gravity can cause light to bend. And so he tried to go do an experiment, and the problem with it is he needs a light source, and he needs a big enough bending, because light moves really fast. It'll get across this elevator without moving much. He needs it to go a long distance and have something really big to bend it. What he needs is a star in outer space, and he needs that light to go by the sun. But the problem is, when he goes by the sun in the daytime, why don't you look at the stars in the daytime? You can't see them, right? So he needs the sun to be there with its mass in gravity, but he needs it to turn off its light. And he does this with a solar eclipse. And you actually see the bending of light. And that's when he got famous. He did his work in 1905. He got famous in 1919, 1920, because that's when they experimentally finally verified his work. I'll let you guys read that. We'll move on next time. If you got any questions, send me an email.
Dr. Marvel, didn't he originally try to do that in 1914, and then World War I broke out?
Crimea, and his astronomer from Germany was arrested
by the
as a
Russians,
spy,
yeah.
and they took all his equipment. Yeah. You can read God's Equation, which is a little art book that talks